Hi there, this is Dr. Matthew J. Traum, Chief Executive Officer of Engineer Inc. out of Gainesville, Florida, United States. Sadly, I can't be there in person to give my presentation, but I've arranged to give this video talk to describe to you my conference paper, which is entitled Tiny Tesla Turbine Analytical Performance Validation via Dynamic Dynamometry. I'd also like to acknowledge my co-author on this research, Dr. Hope Weiss, who is with the Mechanical Engineering Department at California State University, Fullerton. My company, Engineer Inc., makes laboratory equipment for remote learners taking courses online. So the idea is we miniaturize laboratory equipment, put it into a box, ship it off to a remote learner. They then unbox it and they use it to run hands-on experiments to complement their online learning. So for me, Tesla turbines are interesting for thermodynamics and energy education. But they're also interesting for research. The interesting aspects of them include the following. So the ease and low cost of fabrication, the robustness of Tesla turbines. They can process gas, vapor, liquid, or even mixed phase working fluids without damage, which is great when you're running an environment like mine where the students are remote, and so the teacher is not there to tell them not to do certain things. Tesla turbines are quite robust in those situations. They also run on energy sources that are available in schools and home shops. So for example, compressed air, pressurized water. I even had students build a home-built boiler out of a pressure cooker and run wet steam through one of their Tesla turbines without any damage. No combustion is needed to get them running. So those are the educational benefits. But from a research perspective, Tesla turbines are also quite interesting because as they shrink, their efficiency increases. So I think there's an opportunity here to use very small Tesla turbines for battery replacement in mobile electronics, for example. With the benefits also come some challenges to Tesla turbine adoption. So power produced by Tesla turbines comes at relatively high rotation rate and low torque. What that means is that they're poorly matched to available commercial off-the-shelf dynamometers. In my world, that's hobby scale dynamometers that are meant for RC cars. In my experience, Tesla turbines don't produce enough torque to even spin up a commercial off-the-shelf hobby scale dynamometer. So I've had to build my own dynamometers, which is quite expensive, which negates the cost benefits of using Tesla turbines to begin with. In addition, at least until recently, there's been a lack of reliable analysis tools to predict Tesla turbine performance based on geometric and input parameters. So in my case, I'd like to design a Tesla turbine. I'd like to choose the inner diameter, the outer diameter, the parameters of the flow, and I'd like to be able to know what the turbine's power output is going to be. Up until very recently, you've actually had to build the turbine and test it to see whether your estimations were right. And I've been in more than one situation where I built a turbine and it's been grossly underpowered compared to where I thought it would be, just because I didn't have the analytical tools to design it correctly. So there have been some recent transformative changes. The first is a pair of papers out of the Carey Laboratory at University of California, Berkeley, 2009 and 2010. Carey started with the Navier-Stokes equations and derived from first principles Tesla turbine analytical modeling equations based just on geometric parameters. And then in 2013, I was involved in a project. Lead author was a fellow named Yang, who was a undergraduate research student of mine, and we introduced a technique called dynamic dynamometry that uses the bearing friction and the rotational inertia of the turbine spindle itself, spin up and spin down Tesla turbines, and use that data to determine the power output without need for a dynamometer. So for this research, I wanted to answer a couple of research questions. The most pressing one is, do Carey's technique and dynamic dynamometry agree on what should be the Tesla turbine output power? And can these techniques be applied to tiny Tesla turbines where the viscous effects begin influencing and increasing the efficiency? And for me, tiny refers to Tesla turbines exhibiting laminar flow between the disk channels. So this is a Reynolds number for that flow between the channels, and a value of less than about 2,000 gets you fully laminar flow between those channels. So that's the regime that I'm operating in. It's also the regime where Carey's models were derived to operate in. So from from a theory perspective, we're coming at this from two different directions. So Carey's model, again, starts with the Navier-Stokes equations and reduces it to this equation, which is the velocity difference between the flow and the rotating disks inside the turbine. You can then take this expression, plug it into Euler's turbine equation, and extract an estimated power output for a Tesla turbine based only on geometric and fluid input parameters. From the other side is the experimental approach of dynamic dynamometry, where you take the rotational inertia of the spindle determined experimentally, and then you spin the turbine up and you use the spin up data and the known rotational inertia in this equation to extract a power curve which ultimately gives you the maximum power for that turbine via this experimental technique. So really the question that I'm trying to answer is, does this expression for power from dynamic dynamometry give results similar for this expression for power from Carey's analytical model for a tiny Tesla turbine? So just a little bit about dynamic dynamometry. If you're interested in this technique, I would encourage you to look at my conference paper, look at the reference section, and find my previous papers on this topic, which describe it in much more detail. But essentially what we do is we start with a Tesla turbine. We have no dynamometer. We wrap a string around the turbine shaft, tie a mass to the string, and let the mass fall and spin up the turbine. So that's the spin up process under weight. We then eliminate the mass and put compressed air through the turbine, spin it up and spin it down, spin it up and spin it down, spin it up, reach maximum rotational velocity, spin it down again, and use those dynamic processes to back out both the rotational inertia, which is this equation, and then the power curve, which is the equation that I showed on the previous slide. So we've already done and published this work. Here is an experiment with what I'll call the big Tesla turbine. So here's the Tesla turbine itself. Here's the compressed air supply coming in. And we use a combination of an optical tachometer and a digital timer to get a rotational velocity of this turbine as a function of time as it's going through these dynamic processes. Here is the tiny Tesla turbine that I talk about in the current conference paper. It is 3D printed. It has 4 disks, and the characteristic outer radius of the disks is about 24.85 millimeters. It's about the size of an American dime. Set up the exact same dynamic dynamometry experiment. Here's that tiny Tesla turbine, which is plumbed into a compressed air supply. I use an optical tachometer in combination with a digital timer to extract rotational velocity as a function of time. And because the turbine is so small, I have to use video capture to capture what's going on with the optical tachometer because the processes are too fast to see with the human eye. But nonetheless, they can be captured and analyzed anyway. You just have to use video capture to do that. So here is a typical result from the big Tesla turbine for the spin up and spin down process. So I show time in seconds on the x-axis, and I show rotational velocity on the y-axis. The red squares represent the spin up data where I tied the mass to the turbine and let the mass drop. And the blue diamonds represent the turbine spin down data from maximum RPM. And as you can see, both of these trends are linear. So I just fit curves to both data sets, and those curves happen to be straight lines. So this, up until now, was the extent of my experience with dynamic dynamometry. And so I expected very similar trends for the tiny turbine. And from these similar trends, you can back out, again, the rotational velocity and the power curves. Here's what I got. So again, time in seconds on the x-axis, rotational velocity on the y-axis. This is now that tiny Tesla turbine undergoing a dynamic dynamometry experimental exercise. The spin-up process is linear, as it was with the big turbine, but the spin-down process follows what looks like some sort of exponential decay curve. Now, certainly here at the end of that curve, the process looks quite linear, and so I might be catching the linear part of that curve here with the big turbine. But with the small turbine, I get all the way up into this range where I've got this exponential decay, and that exponential decay prevents me from making a direct calculation of the rotational inertia I of the turbine. So we'll talk about that in a bit. Just as an example, this is previously published work for the big Tesla turbine power curve. I've got angular velocity on the x-axis. I've got power output in watts on the y-axis, a constellation of experimental data points, which I curve fit with a polynomial model. And the theoretical power curve out of dynamic dynamometry is a solid red line. And as you can see, those two curves are quite close to each other and predict the maximum power output quite well. So if I can get dynamic dynamometry to work for a tiny Tesla turbine, I should be able to predict its power output without need for a dynamometer. But I've got that problem with rotational inertia. So again, using the big Tesla turbine, the spin up and spin down plots were linear, allowing me to calculate the rotational inertia directly. But with the tiny Tesla turbine, the spin down was nonlinear. And so I first had to scratch my head and try to figure out why that was. And I think there's two elements to it. The first is the bearing friction. So as the turbine gets spinning very, very fast, the bearings put more and more resistance on that spin process and slow it down faster. But I think the real effect, the much larger effect, is that there's shear between the turbine discs and the non-moving housing. And as the turbine is spinning really fast, that shear puts a very large retarding force on the turbine spindle, hence the exponential decay. So I was unable to extract rotational inertia directly because I didn't have linear spin down data from dynamic dynamometry. So to calculate I ended up actually taking that tiny turbine apart, measuring all the components, and calculating I geometrically. This ended up giving me a bound on I, a lower bound on I, which we'll talk about in the conclusions, what implications that has. And as I said before, I think I can use the linear portion of the spin down curve to back out an I value for a tiny Tesla turbine, but I'm not sure yet. That's a work in progress. Once I have that geometric value for I for the tiny Tesla turbine, I can again apply dynamic dynamometry, the equations for power, and extract a power output of 0.22 watts. Carey's model for the same turbine gives me 0.077 watts. It's a difference of 37%. And even considering the experimental uncertainty in both of those values, they do not agree with each other. But as I said, I didn't really have a good handle on the rotational inertia, I, because I had to measure it kind of just through the geometry. And so it was really a bounding assumption on I. And if I can get a better value of I, it'll actually push the tiny turbine dynamic dynamometry value down towards the Carey model. So because these two things are so close and they're moving in the direction that puts them even closer, I think this motivates additional study. So a couple of conclusions. So certainly we compare the experimental power output of a 3D printed tiny Tesla turbine via dynamic dynamometry and Carey's model. For the Tesla turbine that I described, Carey's model predicts a power output of 0.77 watts. Dynamic dynamometry predicts 0.122 watts, the 37% difference. But the assumptions that were put into both Carey's model and the dynamic dynamometry approach were bounding assumptions, which will essentially push the two results together if they're done more carefully. Interestingly, the tiny turbine spin-down velocity was not linear, which differentiates it from the previous results that I got for spin-downs from the big Tesla turbine. I think this result is caused by fluid shear between the discs rotating next to the fixed housing. And what that suggests is that there is some turbine speed, size, and disc count threshold somewhere beyond which this phenomenon becomes non-trivial for Tesla turbine performance. And so as those turbines get smaller, this becomes a larger and larger retarding factor, which is something that we're going to have to take into account if we're interested in studying small Tesla turbines, for example, for MEMS power applications moving forward in the future. In terms of the use of dynamic dynamometry for educational labs, which of course is my application, it can't yet be used for remote learners until I get a better handle on a good experimental technique to find I, the rotational inertia. So that is a work in progress. I'm hoping to use the linear portion of those dynamic dynamometry spin-down curves to do that, but I haven't done it yet. So stay tuned and we'll see where that goes. Okay, with that, I will bring my conclusion to a close. Thank you very much for your attention. And I will be available, I think, live via a GoToMeeting connection to answer questions. So thank you, and I look forward to speaking with you here in a moment.